Hey everyone, I'm here with Dr. Bing Li, one of the AI spatial research mappers here at Clemson University at the International Center for Automotive Research. And today Dr. Bing Li is going to tell us a little bit more about what his research goals are and what he's doing here at Clemson University.
Hi everybody, today I'm very glad to introduce about my research. I'm directing the Auto AI Research Lab. I mainly work on the research robot vision and learning, specifically how robots perceive the world and also how robots learn about environment to take the action.
Okay, great. Tell me a little bit more about your research. Let's dive into it and let's talk a little bit about the applications and what your goals are.
Okay, great. Yeah, so first I'm going to show you a research currently I'm working on. So the research project is called Spatial AI Real-Time Mapping for Off-Road Autonomy. So we are working on the research to unify the spatial data from perception sensors through the AI. So to build the maps to enable specifically for the off-road vehicles and the operators.
And so I'm seeing here perception and AI. Tell me a little bit more about the need for perception and understanding what perception is and how you apply it with AI mapping.
Yeah, so nowadays we can see that AI has become very powerful to understand the language and understand the images. But still there's a challenge for AI to understand about the spatial world. So we are developing the AI models, specifically AI and spatial data processing models to understand the information of the geometry, understand the contextual information of the surrounding 3D space. So ultimately, the representation of those learning is going to be represented as a map to be used for the robot and also for human operators.
Okay, so perception is basically the sensors to understand the physical 3D space and creating that like digital map for robotics or vehicles to navigate in the real world.
Yes.
Okay, and tell me a little bit more about what this map is, and I think you have some PhD students working on some of these areas, so tell me a little more about that.
So on the bottom right, we are working on a technology called SLAM, simultaneously localization and mapping. We are developing the AI models on top of the SLAM model, and then to have the algorithm is able to understand the location of the robot and also build the maps for the surroundings to allow the robot to take the actions. So one of my PhD students is working on the SLAM algorithms.
So the traditional SLAM methods, they lack in performance when it comes to large scenes and in complex environments and or like dynamic environments. So what we're trying to do is we're trying to incorporate artificial intelligence, AI tools to the traditional SLAM methods to improve its limitations.
How is AI integrated into the SLAM protocol or methodology, and how is that creating a benefit?
Sure. For example, we're using some learning techniques, specifically self-supervised learning, and we're incorporating those to the traditional SLAM parts, such as, so one aspect will be like place recognition, for example. While it's doing the iterative localization and mapping on the back end, it needs to fix some estimation errors and fix its global trajectory, and needs to previously recognize previously visited places. Mm-hmm. So for that place recognition, for example, we incorporate some learning techniques to make some of these tasks more feasible. And one other area we're looking at is, for example, like depth estimation. For example, okay. If you're just working with cameras, then you need to perceive and estimate depth. And those could have some errors, but by incorporating the AI tools, we're kind of learning from the mistakes and having more generalizable systems.
The image we're showing, this is the AI map. So we are working on the spatial AI model maps, the models, which is able to unify all of the captured perception sensor data and then to have a map representation. So this map is a very high fidelity map.
So as you can see, this is the video that I took by my drone, and then I actually making like a 3D Gaussian like a model out there, and you can see it's pretty like high fidelity.
Is AI used in your research, and how is it used?
Yeah, so like for this model, we get the video, we take the frames from the video, and then we put it into like a code map, which we generated the point cloud. But if we are not using code map, we can just combine with the neural models like networks. So they have the probably the same performance as the code map, because code map to processing this video is probably take 4 or 5 hours, so it's really long. But if you combine that things, if you just use all the input to like a network model, and then it will give you the same things, maybe probably you just within like half hour or something.
Oh wow! So
Yeah.
you basically take the processing time from something like 4 or 5 hours down to half an hour. I mean, I see like long term, like most of the planet is actually a natural landscape. It's not roads. Like
Yeah.
roads are great if you can
There's
like
no roads.
pre-program everything for the roads, but most of the
Exactly.
world undersea, on terrain is all uneven surfaces, and we eventually need to get to the point where we can use these tools for automation and self-driving and robotics in a non-controlled environment, which is like a natural landscape, which is like 99% of the planet, actually.
Yeah.
When I kind of like process what you're saying and kind of bring it back to how humans perceive the world, like our eyes are a sensor to understand the visual field in front of us. And then in our brain, we kind of map all the things our eyes see into a 3D space so that we can walk around in a 3D space or we can navigate. And you're kind of doing the same thing with 3D systems, mapping in AI to create that digital space so that the robots can navigate, much like a human does with our eyes, using that as our sensor and perception.
Yes, that's what we call the spatial AI. So we try to use the AI and then develop the spatial AI models to understand the spatial 3D space. And the 3D space can be as a representation to empower the action of the robot.
Okay, great. And I see you have another image down here. Is that one of the other PhD researchers you have that are doing work?
So he's working on the simultaneous localization and mapping SNAM algorithms. So specifically, he has been working on the LiDAR 3D SNAM, and then to build the 3D geometric models for the environment. And also, he's working on the AI models for the SNAM to improve the SNAM accuracy. As we know, off-road driving is very challenging, and specifically, my research has been focusing on physics-informed perception and learning for the off-road driving. It's very unstructured. So we wanted the perception model is able to capture all of the geometric information, even including some of these unseen areas. For example, some of the occluded areas. So we are developing the perception models, which is able to fuse the continuous frames and also learn from the data. Ultimately, the perception models is able to predict and learn those geometric representations, which can serve as a base for the autonomous driving in the off-road for the decision making. Another part is about the physics informed. So we not only understand the geometry, we hope the perception models is also able to understand the semantic, for example, different kind of terrain, and also what kind of physical potential properties of the terrain. So those kind of recognized information is going to be part of the input for the decision making. And then that comes to the stochastic control, and which means the probabilistic uncertainty representation of the environment and also for the vehicle states. So those kind of states and also environment states uncertain representations is going to serve as an input for the control algorithm and also control models. One of my PhD students is working on the learning-based control, especially for those kind of off-road driving environment.
From this actual data, so this is the sensor data, this is from a camera, and this is from a depth camera. So depth camera gives you the depth values.
Okay.
So combining these two sensor data, we build a representation of the environment. So this is the actual representation of the environment. We simplify the environment, we abstractize the environment, and usually those robots work on a 2D environment. But when you talk about off-road, the challenges grow exponentially. One of the biggest challenge is the terrain is uneven. Other challenges is that the terrain is highly dynamic. As you mentioned, the friction value changes. So all these factors make the problem very challenging. And part of my work is how do we tackle these challenges and build robust autonomous navigation systems for off-road vehicles. So by interacting with the environment, the robot learns what's a good action that will bring a good reward to it.
Yeah, which is actually very similar to how human beings learn.
That's
right?
true. That's
like
true.
if a child gets disciplined, they learn that that's bad. If
Yeah.
they get rewarded with candy, they learn
Yeah.
that that's good, or praise or love, that's good. So there's a lot of like concepts that we're bringing in from human experience and for neurochemistry in the human brain to the AI systems and the neurologic we do for these machine learning and AI systems.
That's true, and that's at the core of artificial intelligence. And this particular technique is called reinforcement learning. But there are multiple techniques, and specifically reinforcement learning is how we learn through our experiences,
Yeah.
through the rewards and the punishments that a child gets.
Yeah.
So the same thing the robot does here.
There are two parts. So first, we can train the model through the simulation. And then for the real world experiment, we still is going to collect the data from the real vehicle. And then those data is able to be used to fine-tuning the model so the model can perform better in the real world scenarios.
Okay, so the real world data, like data that you collect outside of the building and in a test track or something like that, use that to refine the simulation model and then rerun simulation models and use those outputs from the simulation models to train the data.
Yes. Okay, another research I would like to show you is about the digital design with the AI agent. So nowadays, the digital design has been used a lot in a lot of the scenarios like manufacturing and also in a lot of the simulation scenarios. So one of the gap what we see over here is if the AI is able to understand the 3D spatial data, has a 3D spatial intelligence, and how the AI can help with the design process. So for example, when we do the traditional design, so we kind of like visualize the data and then grab the model, draw the model, and then perform stat-alone simulation. So what happens if we have an AI agent to help us with that? So first, so we can capture the 3D spatial data through the perception sensors, and then the AI agent is able to understand the 3D spatial data. And the AI agent is also able to make a decisions, take the actions during the digital design world. And ultimately, it's not only for the mechanical design of the vehicle, but also for the autonomous vehicle algorithms, for the validations. So we hope to unify the digital design and AI agent together so we can have the AI agent to help us, human beings, to design better machines, better robots, and vehicles.
Okay, I know AI agents is a really big exploding field right now in a lot of applications. Large language models and ChatGPT has become very, very popular in recent years, really recent months. And this seems like it's another application of using an AI agent for this spatial data in a digital design domain. I've worked in engineering where we have a lot of siloed different engineering disciplines. We have electrical engineers, we have aerodynamics engineers, we have chemical engineers, we have material science engineers, and traditionally and currently I think when you are designing a car, designing a system, you have all these different siloed engineering disciplines and simulations and different simulation software packages, and they all have to be done separate.
Yeah, separate systems.
Separate systems and separate people and separate disciplines in a whole group of people. And what I kind of hear you saying is that with an AI agent, you're able to kind of synthesize all those different disciplines into one kind of digital domain where they'll help you do all those kind of like back-end calculations and simulations in real time so that you can design a vehicle, validate a vehicle, all kind of in one space instead of having to send it out to different people in different departments.
So we wanted the AI agent is able to access those digital contents and also is able to access all of those engineering knowledges, so which can give us some of the prediction answers about the design. And the main role in the human is we can interact with the AI agent and then to give what kind of design requirement we expect. And also when the AI give us some of the suggestions, the designer is able to validate the prediction to see whether it complies with physical laws.
That's the physics-informed aspect of it.
We wanted to ensure the design, everything, the physical system is able to compare with the physics systems.
In the real world. Okay, and I see here a couple photos on the right here about research, education, and outreach. Let's talk a little bit about what kind of education outreach activities you're involved in.
One of the main efforts we are working on is about the driving safety. So nowadays, with the vehicle become more and more intelligent. So sometimes the new drivers, for example, for the teenagers, they tend to be pretty easy to overtrust the vehicle, which is a big risk. So we have been, over the past few years, we have been doing the summer camp. I'm teaching the summer camp class called Driving Safety in the Array of Intelligent Vehicles. So in the camp, we introduce different kind of new ADAS features, and also we compile all of the materials about the new ADAS of different kind of vehicles, and then we put it on the website. So people around the world is able to access. Specifically for the teenagers, they can better understand what kind of new features, what does that mean, and how the AI works for certain detection, perception detection, what kind of scenarios the algorithm is going to degrade. So in that case, as a new driver, instead of just trust on the algorithm, trust on the AI to take over the driving. So the new drivers can also be pay attention for those kind of challenging scenarios, or even take over for the control for the vehicle to better to guarantee the driving safety.
Kind of bridging the gap with these advancements in technology and the risks that it's creating for drivers, especially young teenage drivers.
Yes.
Very cool. Okay, let's go on next and let's talk a little bit more about, I guess, some of the applications for your research and where you envision this research impacting science, technology, and society at large.
So the research my team is working on has a broader impact on different kind of fields. So those perception results can output as the 3D reconstruction models, can have the map representation of the target, so which can help the machine to make a decision. Another research is about the 3D perception, so we are working on those perception, ADAS, and also for the driving safety. And we hope to better to improve the driving safety and also develop the new capabilities to enable better ADAS features. And from the digital design and agent AI perspective, so we hope those design paradigm through the AI agent can help broader robot and vehicle design. So we wanted to facilitate the robot and vehicle design. Ultimately, we can have the AI agent to help us to design those systems and also comply with engineering and physics laws.
So really taking advantage of emerging technologies in computer science, advancements in computer science, and finding new applications for those advancements in computer science and robotics to apply towards autonomous driving, 3D mapping. And then I see here you also have aerial ground vehicle systems. Tell me a little bit more about how expanding the perception to an aerial vehicle helps with these ground systems for off-road vehicles.
Yes, so basically one component is about the ground vehicle, right? Another component is about the environment. So to help the ground vehicle to better understand the 3D environment, and especially in some of the large scale or high speed scenarios. So to better to ensure the safety and also the stability of the vehicle, for example, in the unstructured off-road environment, right? So it makes good sense to have the pair with the area system, which is able to capture the larger scale in front 3D space information, and then those information can be represented as the unified map to have the ground vehicle for the decision making. So those has broad impact. For example, we have been working on the golf cart. Certainly we believe the golf cart in those golf carts is able to build the maps and then is able to fully driving autonomously in a golf cart. And the every ground vehicle system can have broad impact, for example, for the agriculture and also for the mining scenarios.
Okay, agriculture, mining, yeah, it makes a lot of sense because if you can extend your perception and gather more input about the 3D space and 3D environment through a drone or an aerial vehicle, that just kind of refines your three-dimensional map for your focused vehicle, either a mining vehicle, agricultural vehicle, or self-driving car, or whatever the application is.
Yes, so basically we are building the state-of-the-art 3D vision algorithms and also AI models. So those 3D vision perception play the fundamental role to enable the high-level application of the autonomous robot, autonomous vehicles. And in addition, so we are working on the fundamentals of the spatial AI intelligence methodologies to help the AI to better understand the 3D spatial data, 3D spatial models. So this not only help the autonomous vehicles to make a decision, but they can also understand the 3D, the surroundings, understand the 3D spatial context. So those data can be served as an input to feed into the AI agent, because nowadays leverage on the state of the art of the AI. So the AI agent is a certain intelligent agent which is able to interact with the environment and also have the 3D perception, and ultimately is able to give the decision making to help our design, to help our vehicle and robots.
This is very exciting research, and if potential students in the future want to learn more about your research, if they're interested in AI agents, 3D spatial mapping, autonomous vehicles, and all these broad applications, where can they find more information? Do you have a website? I think you have a QR code you can show, and they can get a hold of you, they can learn more about your research, and they can kind of go from there if they'd like to learn more and maybe apply to come to Clemson University.
Yeah, so basically I'm putting the research and also research publications and some of my research videos in my lab website. In addition, if you have any questions or would like to do any of the outreach activities with me, feel free to reach out.
Okay, thank you so much, Dr. Bing, for sharing some of your research. This is very exciting stuff, and I'm looking forward to seeing where all the broad applications end up going with the outcome of your research. It's exciting.
Okay, thank you, Luke.
Thank you very much. Okay, thanks.
Thanks.
Thanks, everyone.
Thank you.